Okay, welcome back to this video series on guitar distortion. So today we are actually going to look at putting some input signal into this pedal, and we will be putting in a pure sine tone at 500 hertz, and then looking at the output. So we're basically just looking at, amplitude over time right now. So we're not doing any kind of like FFT. We're just trying to see, if we put a sine wave in, what does the output waveform look like? When people talk about clipping, what does that actually look like, and rectification? So yeah, we'll get into that. But before I do, I just want to give you a little bit of kind of a plug for a very cool program called Room EQ Wizard. So right now I'm using it for its test tone generation here, and also its oscilloscope tool. So if you haven't used this program before, it's very powerful. It is free, but you should donate to it if you can. It's called Room EQ Wizard, but I feel like it's kind of taken on a life of its own of many audio analysis purposes. So yeah, it's great for measuring room acoustics and tuning in loudspeakers into rooms and corrective EQ and all that stuff. But it actually finds a great purpose as just a general audio analyzer, which is what we're using it for today. So if you have a audio interface, you can just go into preferences and set up your device and what inputs and outputs you want to use. You can calibrate it. I don't currently have this calibrated, but I don't think it's a huge problem at the moment. What I do have calibrated, though, is the input and output levels. So, for instance, I just want to show you so I've got my generator here, and I am going to, let's go ahead and look at our scope at the same time. So if I, go ahead, put this tone in here, basically the signal flow of this is out of this signal generator. I go out of my audio interface, and I actually have this little reamp box that's kind of out of focus right now, but whatever. And that basically takes the low output impedance signal from my interface and turns it to a high impedance signal that will then go to the distortion pedal right here. So the reason you want to do that is because you basically want to load the input of this pedal the way that a guitar pickup more or less would. So anyway, so let's look at what this actual signal is here. So this signal is my, guitar. It's just a pure tone. It's not guitar, but let's go ahead and just measure what that is. So, and we can look on my multimeter. Okay, so yeah, I've calibrated this to 100 millivolts, and this is a RMS. Okay, and then at the frequency of 500 hertz. So yeah, we're getting the signal we intend. So that's good. So, all right, Windows, don't do that right now. So we're going to take this 100 millivolt, 500 hertz signal, and we're going to put it into our pedal. And right now I don't have the switch turned on the pedal, so it's just going through the bypass. And then, you see it here at the oscilloscope. So you can see here that the peak is at 145 millivolts at the top, and then the bottom is also 145 millivolts. So that's the peak voltage. And so if you wanted to convert that over to RMS, let's just do, we said 145 millivolts, I think. And if you just want to go from peak voltage to RMS, you just divide it by 1.414, and, whatever, close enough, 102 millivolts RMS. So the way that you actually calibrate this signal on the Room EQ Wizard side is you actually need to, if you've got gain on your, mic pre to your interface, you can actually look right here at the input. So I know from this, meter, that I was putting 100 millivolts into, the pedal, and I had already done a loop back to calibrate this without the pedal in line. And so, I can just kind of move the gain on my mic pre around until it's calibrated. And then I know what I'm sending out and coming in are these known values. So, anyway, this is not a Room EQ Wizard tutorial, but it is a great program for, analyzing audio systems, and we can put it to use here today. So, all right, so we're calibrated, and let's go ahead and turn our pedal on here. So we know we've got that 100 millivolt, 500 hertz signal coming in, and we're just going to turn on the pedal, and there you go. So here's the bypass, and the pedal turned back on. So just watch the amplitude shift, and also just the shaping of the waveform change. So very different. So we basically have taken a sine wave and turned it into this kind of asymmetric square wave. So let's just talk about a couple of these features that I'm seeing here. So let's kind of readjust these cursors, amplitude cursors. Okay. So before we were at like 145 millivolts peak, and now our positive swing is at 660 millivolts. And it's not, this nice sinusoidal curve. It's very much a square wave with all these little harmonics over top of it. So we can see, we're getting just overall gain boost, but we're also clipping the waveform a lot. So this is where that term comes from, clipping. We're literally just clipping off the top of the waveform. And so on the negative side here, you can see a similar behavior. You get all this clipping. You don't get the nice sinusoidal curvature. The thing that's interesting here is this one at the positive is 660 millivolts, and this is 430 millivolts. So there's actually kind of this asymmetric gain that happens between the positive swing and the negative swing. So that's what we call rectification. So we've got two kind of signal characteristics happening here. We've got the clipping, right? We're just taking off the top of the waveform. And then we've also got this rectification where, we actually see more amplitude on the positive than on the negative. And so these are two kind of critical, features of how we create distortion and what type of distortion you actually get out of that. So if we are, just doing, let's just say this was symmetric clipping, where we had 660 millivolts here and 660 millivolts here. That is actually just going to generate odd ordered harmonics. So if we were to normalize this 500 hertz sine wave to 1 hertz, we would actually see harmonics happening at 3 hertz and 5 hertz and 7 hertz and 9 hertz and so on. So that's that kind of hard distortion sound. And rectification, where we're giving that kind of biased gain on one side versus the other, is actually going to generate even ordered harmonics. So if we, again, thought experiment, scaled everything back to a 1 hertz signal, we would see harmonics at the 2nd, 4th, and 6th, and 8th frequencies. So yeah, what else do we have here? The other thing you can see is that this time scaling here between these bars is about half a millisecond. So whatever, 500 microseconds between here to here. And so we can see, like, we know we've got a sine wave that has, symmetry in the time domain, right? The rise time, fall time in that waveform is the same, but in our distorted signal here, you can see that, we're in the positive swing, we're high for 750, microseconds. And then over here, we're low for 140-ish, or I'm sorry, 1.4 milliseconds. So there's kind of like almost a, not quite doubling of time between the positive and negative, but it's spending more time, going low than it is high. So that's a really interesting feature of this pedal. So yeah, I think that's enough for this video. So with the first video, we dug into this pedal and we listened to it, so you can kind of get a feel for what the distortion actually sounds like. And so now electrically, we can look at what the output looks like. So you can start to kind of marry those two, the sound and what it looks like on a scope. You can kind of piece that together in your head. So next time, what we're going to do is we're actually going to start talking about transistor amplification and some kind of basic circuits that this incorporates. And we will, kind of start diving into the schematic and how we actually achieve this clipping behavior. So yeah, all right. Well, thanks for hanging out, and I will see you next time. All right, later.